Alright, so we are looking at partial fraction decomposition, which is just buckets of fun. And so first we're going to look at some review of some long division, and then we're just going to do some problems. Yeah, solving these things is kind of like systems of equations, which is fun for some people. If you like the algebra thing, it really motivates my desire to use linear algebra techniques, called like Gaussian elimination, using row operations. But, you know, if you want to learn more about that, then take linear algebra. It's buckets of fun. But, so, partial fraction decomposition, and I also recommend that you check out Paul's online notes for this topic. It's really good. I think I put a link in here somewhere. So, which of these can we solve, and which one can we not yet? There's one of these integrals that we can solve, and one that we can't yet. Do you think it's the left or the right? So, looking at what we have, I think, like our general idea that we could, like, find integrals of things was if we had our derivative, that gives us, like, the natural log of our, if we have a derivative over our not derivative, then that's going to give us a natural log, and like plus c, this kind of thing, right? So between these two, I say if we have u is x squared minus x minus 6, then du is going to be 2x minus 1 dx, and that's right there. So that means that this gives us integral du over u, so natural log of u plus c, and that's natural log of absolute value x squared minus x minus 6 plus c. And this one we do not know yet, so heck. Oh, the joke didn't land in the right spot. Oh, this is so sad. Okay. Boom. We don't know. But that's okay, because we can figure this out after we do some partial fraction decomposition. So, let's look at the partial fraction decomposition for these different problems, and you can click here for more. Oh my gosh. For more on that. But try to recall in your brains how we can do partial fraction decomposition, and then we will walk through some of these. But try at least one of these on your own, and then we will work on it together. So if we're looking at the first one, the goal really is to have our denominator in factored form so that we can rewrite it as one factor in the denominator plus another one of our factors in the denominator. So if we have x squared plus 3x minus 18 in our denominator, that means that we factor that to get what? X plus 6 times x minus 3, and that's our 8x minus 42. And then we can rewrite this as something over x plus 6 plus something else over x minus 3. And so now we have an equal sign that we are forcing to exist, and we are going to try to make these equal, figuring out what our a and b need to be in order for these two to be equal. So, well, we can just multiply by x minus 3 for the first term, and then multiply by x plus 6 for the second, and then we just get our common denominator of x plus 6 and x minus 3. Okay, that's nice, and that equals 8x minus 42. So then we have that is over x plus 6 times x minus 3. And then we have 8x minus 42 equals ax. And if I just multiply everything by x plus 6 and x minus 3, as long as x isn't negative 6 or positive 3, so x can't be negative 6 or positive 3, then we're okay, because we don't break our denominators. So we have 3a's here, negative 3a's there, and then bx plus 6b's. And so we can group these with our x's together, so 8 equals a plus b, and then our constant terms, negative 42 equals negative 3a plus 6b. And then you can think back to algebra, where we're like, okay, so how can we combine these two equations to solve our system of equations? Probably multiply everything on the left and the right by 3. So then we get, our first equation is 24 equals 3a plus 3b, and then negative 42 equals negative 3a plus 6b, and then we add these two together, we get negative 28 equals, is it negative 28? Positive 24. It's negative 42. No. 18, right? And then we get 3b. So then we end up with b is negative 6. Wait, hang on, I did bad algebra. I added 3 plus 6 and I got 3, and that doesn't make sense. 3 plus 6 is 9. Okay, so that gives us b is negative 2. And then we have 8 equals a plus negative 2, and so then a is going to give us 10. So then our partial fraction decomposition for a, part a is, this is a 10, and that's a negative 2. 10 and negative 2. And why would we want to do that? Well, integrating this is way more annoying than integrating that, right? Because this is just 2 natural logs, because that's the goal. Just getting natural logs. Alright, cool. Shall we do another one? Yeah. Which one should we do? I guess we should do B. Let's look at B. I wonder if I could copy it and then paste it down here. Does that help? Not really. Okay. Well, we'll try it again. Here we go. So, how do we do partial fraction decomposition for this? Well, we need to factor, right? So our denominator, this 2x squared plus 7x minus 4, we can factor that, so we get 2x, those 2's, and then a 4, so we got a x here. I should probably change colors. Okay, so let's see, we get 2x minus 1 and x plus 4, so that'll give us 2, 8, minus 1 is positive 7, negative 4, okay. And then that'll give us a and a b. Why do we use capital A and capital B? It's just like convention? I don't know, it's a good question. Maybe you can journal about that. So this means that the 9 minus 9x is going to give us a times x plus 4 plus b times 2x minus 1. And you may be thinking to yourself, hey, well, this has to be true for any x. So suppose I just declared, suppose I just said, let's say that x is negative 4. So if x is negative 4 and you plug that in for x there, and there, and there, then the equation still needs to be true. And that's absolutely correct. So then we would have what? 9 minus 9 times 4 is 36, but negative times negative is positive. And this equals, and that forces all that term to go away. So then we get b times negative 8 minus 1. So then we get, what, 45 equals negative 9b, therefore b is negative 5. And then we can also use just like our a plus 2b equals 9, right? Because we have 9 here, ax there. Oh, wait, sorry. We have 9 there. We have 4 a's there. So we have 9 equals 4 a's and negative b. And then we have our b that we can sub in there. So we get 9 equals 4a plus 5. So then 9 minus 5 is 4a. 4 equals 4a, and a equals 1. So we have a is 1 and b is negative 5, which we get a is 1 and b is negative 5. And boom, there you go, a partial fraction decomposition for this rather extensive rational expression. All right. And if you want to look at these, then head over to Paul's online notes. So, how are we going to evaluate this? Well, we should probably decompose our integrand. So, what does that give us? We have x minus 3 and x plus 2. And we have a and b as our numerators. So we have a times x plus 2 plus b times x minus 3, and this gives us 3x plus 11. And you notice I'm being lazy and not writing the denominators, and that is okay. So that means that we have 3 with our x, and that equals a plus b. And we have, so that's nice for later. Maybe we can try the plugging in trick. So if we just plug in let x equals 3, then this all cancels. We have 3x plus 11 equals a x plus 2. So then 11 plus 9 is 20, and that equals 5a. So a is 4, and that means that b is negative 1. So we have our partial fraction decomposition with 4 and negative 1. 4 and negative 1. And so we need to integrate that. And that is not terrible. What do? We have 4 times the natural log absolute value x minus 3, and then when you chain rule on that, there's nothing left, and then plus negative natural log absolute value x plus 2 plus c. Boom. Cool. It's not so bad. Whoops. There you go. So what about this? Well, the denominator looks worse, and our numerator suddenly has an x squared term. So, yeah, let's see how we can fix this. So let's try factoring the denominator. It's probably a good starting point. So we have x, right? We can factor out an x from all of this. So we have 3x squared plus 4x minus 4. And then that, I think, we can factor again to give us 3x and an x, right? Because 3 is prime. And then would 4, will we want 4? No, we don't want 4 because that won't work. We probably want a 2. So we want a 2 here and a 2 there. And then we want the positive 4 in the middle, so we need the 3 times 2 to be positive and the negative 2 to just be there. So then we end up with positive 4. So then we have what? 3x minus 2 and x plus 2 as our different denominators. And then we can do a, b, and c here. So now we can just like multiply through so we can get our terms to be the same. X squared plus 4 is going to be a times 3x minus 2 times x plus 2 to get these two denominators. B is going to be x times x plus 2 because it's the other denominators. And c is going to be x and 3x minus 2. And so suppose we say x, let's say that x is 0. Why is x 0? Because that means that both of these terms go away. And so then we have 4 equals a times negative 2 times positive 2. So a is negative 1. That's nice. What else can we do? Well, we could also plug in x equals negative 2. So if we let x equal negative 2, that means that this goes away and this goes away. So then we're left with negative 2 squared is 4 plus 4 is 8 on the left side. And then we have a c times a negative 2 times a 3 times negative 2 minus 2. And so that gives us 8 equals negative 8 times negative 2 is 16. So 8 over 16 equals c, or c equals 1/2. Okay, and then what about our last thing? Well, that too. So how do we get b? How can we figure out what b is? Well, we can do the same thing where we plug in 2/3, right? So let's try that. So let's move over here. Let's let x equal 2/3. So then this goes away and that goes away. So then we're left with 4/9 plus 4, which is 36/9 equals b times 2/3 times x plus 2 is 2/3 plus 6/3, which is 2. And then we have, what, 40 over 9 equals b 2/3, and what is that? It's 8/3. Our denominators all go away, which is nice, so we end up with 40 over 16 equals b, which is 10 over 4, which is 5 over 2. Okay, so b is 5 over 2. Alright, and let's zoom out a little bit. So that leaves us, our integrand is going to be negative 1 over x plus 5/2 over 3x minus 2 plus 1/2 over x plus 2 dx. And we can break that up into separate integrals. We have negative natural log absolute value of x plus 5/2 natural log absolute value of 3x minus 2, and then over 3 for our chain rule. So then we get 2 times 3 is 6. So this is a 5/6 instead. And 1/2 natural log, I'm just going to sneak over here, absolute value x plus 2 plus c. Boom. There you go. So that's the strategy for partial fraction decomposition. Step 1, you factor the denominator. Step 2, you multiply things through. Step 3, you plug in things to make your life more convenient. And then step 4, you sub those back in and integrate. The more terms you have, the more tedious it gets. This could also be solved not using this plugging in trick if you so desire. You could set up a system of equations. I think you get 3 equations here, and you would get to solve, because you would have a x squareds term equation, x terms equation, and a constant terms equation. It's just a lot more effort. Alright, so got a couple more. Wow, look at that. And we have like a double, we got like a repeated one too. Right, in our factored form. We got a repetition in one of our terms. So, what should we do? Well, we need to account for that like redundancy. So we have a over x minus 4, but then we have some other term over our x minus 4 that's squared. And then for this last part, we're actually, because we have a x squared plus 3, and that's like a term on its own, then we need our numerator to now be cx plus d, because what we have in the denominator is quadratic, so our numerator needs to be 1 degree less. The reason that we don't have a linear thing in the numerator here is because x minus 4 is doubled, so we're just accounting for that doubled. Okay, so here we go. We have x squared minus 29x plus 5, and that equals a times x minus 4, because we just need one of those, and then x squared plus 3. We got a b that's only multiplied by the x squared plus 3, and then we have a cx plus d that's being multiplied by x minus 4 squared. So that leaves us with, we need to kind of group our terms together. So we have x squared, and that's going to give us a times negative 4x squared, right? So that's going to give us a negative 4a x squared. And then our b is going to be, oh, there's actually a secret, another one, because there's nothing with x cubes, but we do have cubed terms. So we have ax cubed and cx cubed. So that means that there's got to be 0 of these. So that means that 0 equals a plus c. Okay. And then for our x squareds, we have one of those. And then how many of these do we have? We got a bx squared here. And then we have a dx squared. Oh, there's also the c. Yeah, because we have the x minus 4, which is x squared plus 8x minus 4, minus 16, sorry. Minus 16 plus 16. No, minus, oh my gosh, x minus 4 times x minus 4 plus minus 8 x plus 16. Whew. Okay, so then we also have a minus 8 cx squareds. Okay, and then we also have, and I guess we should change colors just because it might get confusing, we have negative 29x right there. And then how many other x's do we have? There's 3ax's. There's no bx's. There's 16 cx's. And then there's negative 8 dx's. And then last but not least, we have our constant terms, where we have a 5 from here. And then how many a constants do we have? Negative 12 a's. How many b constants do we have? We've got 3 of those, 3 b's. How many c constants do we have? None, because c is always tagged along with this x. So how many d constants do we have? We have 16. All right. So maybe we should rewrite this 0. So this gives us 0 equals a plus c. 1 equals negative 4a plus b minus 8c plus d. Negative 29 equals 3a plus 16c minus 8d. And 5 equals negative 12a plus 3b plus 16d. So how are we going to solve this? Alright, so in lieu of solving that gigantic system of equations, we are going to use a secret thing, not secret thing, but this is a way of solving systems of equations, and it's nice, and we can use MATLAB to do it. So I made an example, like the matrix name, I called it example, and then this is called an augmented matrix because it's the coefficients for my terms, which are from here. 0 equals a plus c, so a is the first column, b's are the second column, c's are the third column, d's are the fourth column, and then the fifth column is like whatever this equals. So it's called augmented matrix because we have the coefficients and then it equals on the last column. And then I did that for all of these. So we have negative 4a plus b minus 8 plus 1, d equals 1. So that's this second row. And then the third row is coming from the third equation. And then the fourth row is from the fourth equation. And then we use this function called rref, reduced row echelon form. And that gives us this, which means that a is 1. B is negative 5, C is negative 1, and D is 2. So, what was it? A is 1, B is negative 5, C is negative 1, so we have a negative 1, and D is 2. dx. Alright. Well, that's nice. I feel like we can do some stuff with that. So, let's see. Where should we go? Should we go down? Yes, we should. Okay, so from here, that's just natural log absolute value x minus 4. Right? That's just u substitution with u is x minus 4. Here we also have a u substitution with x minus 4. We have negative 5 and then x minus 4 to the negative 1 power with a chain rule that still works. Okay, great. For this next part, I think we should rewrite it as plus integral negative x over x squared plus 3. plus 2 over x squared plus 3. And we're allowed to do that. We're allowed to break up the numerator. That is totally allowed. Okay, dx. So for the left, that's going to be a minus natural log absolute value x squared plus 3, but then we need to also take into account the chain rule, so we divide by 2 to get rid of our 2 that we're going to get multiplied by over there. And then this part, that looks like we're doing arctan, right? Arctan, and we have x squared plus 3, so 3 is root 3 squared. So then that's going to be plus, what, 2 arctan of x over root 3 plus c. And, yeah, I guess we should copy down the rest of it. So this is natural log absolute value. Oh my gosh. Natural log absolute value x minus 4 minus 5 times x minus 4 to the negative 1 power. I don't really care if you leave it like that. You could put in the denominator. It's up to you. Oh, wait, we need to also divide by root 3 here because of the chain rule, right? Yeah. Alright. And there we go. So sometimes your answer with partial fraction decomposition doesn't only result in natural logs, and that is okay. So let's look at this one. What are we going to do? Well, we have the same power, like we have the same degree polynomial in the numerator and denominator, so we could go back to our old friend, the polynomial long division, to get this in a little bit simpler terms. So our denominator is on the outside, and then our numerator is on the inside of the division house. Multiply by 1 to cancel this out, so we get x squared plus 1, and we're subtracting all of it, so we're putting a parentheses because we're responsible, and so that gives us a negative 1 as our remainder. So that's a negative 1 over x squared plus 1. That's what our remainder is. And so this gives us our integrand is instead 1 minus 1 over x squared plus 1 dx. And then that's not so terrible, because x, the integral of 1 is x, and then minus arctan, or inverse tangent of x plus c. And there you go. That's, man, feels like we did a lot. Wait, did we not do that? Oh no, I messed up the sign. Hang on, I copied this wrong. This is a x squared minus 1, so this is a minus here. Yikes. So that changes the sign here to plus, which means that's plus, and our denominator is no longer arctan. So that's annoying. Here, let's fix that. So what do we have? We have plus 1 over x plus 1, a over x plus 1, plus b over x minus 1, because we can factor our denominator, and that's dx. So let's go ahead and solve that. I thought that, yeah, that didn't make sense at all. Like, why would the last example in the partial fraction decomposition now be a partial fraction decomposition? It's silly. Okay, so we have a x minus 1 plus b x plus 1, and that equals, what did we have in our numerator? We had a 1, so that equals 1. That means that when we let x equal 1, this goes away, 1 equals 2b, so b is a half. And when we let x equal negative 1, that means we get 1, and that cancels. So then we get negative, equals negative 1. So we get 1 equals negative 2a. So then a is negative 1/2. So here is negative 1/2. And this is positive 1/2. And so what do we do from there? Well, that we can handle. So the x still comes out. We have a negative 1/2 natural log absolute value x plus 1 plus 1/2. Let's sneak this over. Oops. Natural log absolute value x minus 1 plus c. Boom. There we go. And all this talk of decomposition, this is the tiny soapbox time. And disclaimer, I put it at the bottom, I haven't actually fact-checked this, but this is just food for thought, how long it takes for different things to decompose. It takes a long time. So how long does it take for trash to decompose? Well, leather takes 50 years, which that was like very surprising to me. I guess, like, logically it does make sense. But plywood takes like 1 to 3 years. Plastic bag, like 10 to 20 years. A cup, foamed plastic cup is 50 years. Apple cores are only 2 months, so like unashamedly eat apples and go and, compost them. Paper towels are 2 to 4 weeks. Newspapers, 6 weeks. Plastic film containers, which I don't know if anyone uses anymore, but that's 20 to 30 years. Microfilament fishing line, 600 years for that to decompose. Like, that's wild. So just food for thought. And keep in mind that compostable packages, they will decompose if they are in composting facilities. So if you throw it in your compost pile, I don't think it'll work. But yeah, think about that. I haven't fact checked this though. Alright. That's it.